olivines can be used, because that's what I'm going to do. So the talk of my title changed a little bit, but what I want to go do is go back to Apollo 17 and look at olivine cumulate 71597, work being done at the University of Notre Dame with Clive Neal. And here we have a picture of Jack Schmitt collecting my sample on the moon. And so this is back there. The sample itself is 2 by 3 centimeters or so, and it was first described, when it was first described, the olivine really sticks out. If you can see the green there, that's what it looks like. And it caught the eye of some of the early investigators of the Apollo 17 suites. And Warner in particular looked at the sample and just went to town on it. And they did a major element study and found that 4 main points really pointed to the sample being an olivine cumulate. They started with it has the highest magnesium oxide ratio or content of all of the marine salts from Apollo 17, as well as the highest modal olivine abundance at 19.3%. And it also has a rare earth element profile, which is subparallel to, or parallel to, but lower than the rest of the suites. And the lower rare earth element profile is a consequence of this rare earth element depleted olivine accumulating and bringing down the profile uniformly. In addition to that, they also found a bimodal distribution of olivine forsterite content, where we have here in section from one of my samples, and just for so the higher than 70 forsterite content is in these very large, up to several millimeter size olivines that are, and then there's a gap, and the lower, what they call matrix olivines, are found to have less than forsterite 70 abundance. And there's also a bimodal distribution in size as well. And what's really unusual about this is that you have huge olivines in the sample, and it's also a coarse-grained rock, where normally we don't see that in these samples. And 35 years later, there's really no other high titanium sample that comes close to the extensive accumulation that we see in Apollo 71597. A couple of years after their original paper, Warner et al. Mentioned that it was likely from a type B or B1 type flow, which is just one of the sources of the high titanium volcanism. And Neal et al. Used it in a paper to show that the samples that they studied in the type A, B1, and B2 samples were not olivine cumulates, and also found that the olivine from the sample is far too low for it to be in equilibrium with the whole rock magnesium number. And just a related study using the sample on whole rock oxygen isotopes, Weichert et al. In 2002, used to show that it was typical of Apollo 17 results. And also 35 years later, this is what a picture from 1977 looks like in the record. So I figured it's about time to go back and take another look at this sample. So the research goals that for the study are to do the mineral, major, and trace element geochemistry of the major and minor phases. So far, I have the olivine, ilmenite, pyroxene, plagioclase data collected. Still had some issues with our laser, so I do not have trace element for our malcolite or the melt inclusions. And using these analyses, I wanted to model the crystallization history and also using quantitative textural analyses to model the crystallization history and parental composition, and then tie that in with the other Apollo 17 results, and perhaps and look at if any of these crystals are xenocrysts from multiple megapulses, or perhaps from if it's a cumulate, then if it's just sampling multiple sections from within a flow that's settled out. And so the methods that are used for the quantitative side, crystal size distributions give a plot of length versus population density, and then the slope of that line is a function of the growth rate and residence time of those crystals in the sample. In addition, for major and minor elements, using the microprobe at University of Chicago, and laser ablation collected at Notre Dame. And so had to use microprobe points that were large enough to be ablated. So I didn't do a complete geochemical survey of the sample. We just looked at specific areas of interest. And so for this sample, I have, or for this study, I have two thin sections of 71597, comma 12 and comma 13, just to have things stick out a bit more. So this is the thin section which I showed earlier. We can see they're similar textured. We have huge, large olivines and then several smaller ones stuck around. And then this thin section was rather thin on this side, so I had to avoid that side when doing laser ablation because it wouldn't have lasted. So I focused primarily on 7.5 and 7.12. For our results for the crystal size distributions, the ilmenite CSD is curved and it's typical of other coarse-grained high titanium basalts that we see from Apollo 17. And there's both thin sections there represented as two black lines, generally overlapping the other samples. But what's really unusual is, as you might expect, the olivine CSDs show us something different. It's a kinked CSD where the initial slope is similar to other Apollo 17 olivine CSDs that I've calculated, and after the kink, there's a distinct slope that extends out to a larger crystal size, which is I'll get to that later. And our results for olivine, Warner did a good job back in 1977, and our results generally overlap theirs. We see a bimodal distribution in the cores of the large versus small olivines. And for pyroxene analyses, we don't see the iron enrichment that they showed, that they reported in 1977. I suspect those are on the very extreme rims of some of the pyroxene grains that I wouldn't have been able to ablate anyway, so I didn't analyze those. But what we do see is that for discrete pyroxene grains, there's essentially no iron enrichment, but there's a calcium depletion from core to rim, and all the pigeonite pyroxene are only on mantles of olivine. And our trace element results for some of the major phases, olivine in particular, 7.1597 is shown as black circles, and the cores are essentially the higher forstrate, and then they zone down to lower chromium yttrium. And I wanted to compare these to other suites the other sample suites that I've analyzed. They're not similar to the more primitive type C basalts, but we do see similarity especially in the initial olivines especially similar to the type B2s where they cluster there. Perhaps it's originating in the type B2 type flow and then just showing a continuous trend, or if there's mixing involved. I haven't seen strong evidence for that yet, but investigation is ongoing. And magnesium content in ilmenite is higher, but we don't see any particular distinctions between the chromium hafnium ratio. And then plagioclase is essentially typical in comparison to the other type C basalts. And good, those are all on the same scale. So. And this study was originally titled Melt Inclusions of High Titanium Olivine Cumulate 71597. And I do have melt inclusions, or there are melt inclusions in this sample. I wasn't lying to you. There's also mesostasis just around this one sample, or this one grain of ilmenite that mantles are malcolite, which is very unusual. But unfortunately, right after I wrote the abstract saying that I would collect data, our machine went down until a week ago. So I didn't want to rush those analyses since they're very small and we only have essentially one or two shots at these analyses. But when it eventually comes back online and I go back, the melt inclusions are going to be very useful as they represent trapped liquid at the time of entrainment, and the mesostasis is essentially the dregs of this liquid, and so it can get a very broad time range of the magma evolution. And so the big picture in all of this is that the large resorbed olivines are present at the time of eruption, and using the CSDs at the different distinct slopes, we can calculate that the olivine at their typical growth rates could have been present in upwards of 10 years in the magma chamber prior to eruption, and then the matrix olivine and ilmenite would have crystallized over about 1 to 2 years after eruption. And if 71597 crystallized from a type B1 flow, this may have, if it was thick enough, the type B1 basalts are almost all coarse-grained, and so that might point to this being a very thick flow, which could have, if it's on the order of 10 meters or larger, then that would have been large enough for the origination of a cumulate zone where this sample could have originated. And then, as I said, the null inclusions and mesostasis will further aid in constraining this parental composition. So with that, I'll take any questions and leave you with another big picture.
I have a question for both you and the young lady who gave the talk on the Trocto rock. Since these were collected near each other, but they're so different, is there any clues to where they came from? I mean, we know that there was, the stuff blown out from one crater to a landing elsewhere. Did one come from, say, the east or the west or the north? Any clue that from I guess maybe from the latest satellite, the L rock and such, giving any clue as to where this stuff may have come from?
As far as I know, no. But perhaps if we characterize these rocks, we can use that to identify future sites.
Yeah, and your CSD, that little notch that you had in there, was based upon one particular point. If you left that point out, you would have had a smooth curve. Okay, number one. Number two, I think that you may be overinterpreting the flows, because you have to remember the viscosities of these flows are an order of magnitude less than anything we have on Earth, at least. And that means that almost any flow is going to have olivine cumulate in it. Okay, so it doesn't have to necessarily be a 10-meter flow or anything like that in order to have cumulate in it. So you're going to have olivine cumulates almost every place. Wherever olivine's on the liquid, you have the potential of having an olivine cumulate.
Yeah, those the values for the 10-meter cumulate layer were from Day et al. In 2007. I think they used lunar viscosity in their calculations. What's that? Oh yeah, that's right.
We have time for more questions. Okay. If not, we'll move